isoelectronic. Okay, so all these things are isoelectronic. And then we have this slide, which should be pretty darn familiar since we covered this yesterday. The whole metals form cations and nonmetals pick up electrons, form anions. And then we talked a lot about binary ionic compounds where you just have crisscross and they're monoatomic ions. Okay, and when you crisscross, you're going to end up with a neutral formula unit. So here's an example. So that's in green. Now the next thing is really kind of straightforward too, I think. This idea of what is the size of the cation or the anion relative to the parent atom it came from. So cations lose electrons, and since the electrons are what give it volume, cations will always be smaller than its parent atom. Makes sense? We can say something, make a statement about anions along those lines too. Anions are negatively charged, they pick up electrons, so an anion is always going to be fluffier than the parent atom it came from. So we have an example of aluminum. Here's a neutral aluminum atom, and then when that aluminum atom loses 3 electrons, notice it shrinks. The 118 and 68 are units of picometers. Picometers, right? That's aluminum, and this is sulfur. So we have metal losing electrons, we have a non-metal gaining electrons. Sulfur is a 6A element, picks up 2 electrons to get that octet, or that rare gas configuration. And notice that the sulfide ion is bigger than its parent. That makes sense. Now, especially for part 3 that we're going to knock out Monday, we need to kind of consider the size of an atom, a neutral atom, or the size of an ion basically being created by the electrons, electron cloud outside the nucleus. And what's going on are 2 things. We have attractive forces like attracts unlike, so the electrons are being drawn into the positively charged protons. Negatively charged electrons are being drawn into the positively charged protons. Negatively charged electrons, positively charged protons. And then we have this repulsive force. And, I usually draw this, so what the heck. The repulsive forces with regard to electrons would be fellow electrons. So if we draw beryllium, if we draw a beryllium atom, we have 4 protons in here. I'll go ahead and just go proton plus proton plus proton plus proton. And then 4 electrons out there. So 1, 2, 3, 4. Let's go ahead and give it 4 neutrons. They aren't always equal, but a lot of times they are. And so actually for, that's right. Actually for beryllium, it looks like this. We have 2 electrons in the 1s, and we have 2 electrons in the 2s. So we have these. Okay. So the attractive force would be like each one of these electrons, and I'll go ahead and pick on the valence electrons drawn in. Okay, that makes it smaller. These repulsive forces make it bigger. Okay, so this is bigger. This is smaller. Now I say bigger and smaller, that is to say if the attractive forces increase, it'll get smaller. If the repulsive forces increase, it'll get bigger. So again, kind of remember this little bit of what we're talking about for discussion on Monday. So here we have in the gold are the, let's see, the gold looks like it's what, the parent atom. And then here in the blue, the metals are losing electrons, becoming smaller. Here in the green, the nonmetals are picking up electrons, becoming larger. Yeah. So let's consider 4 things that are isoelectronic with, well, let's see, it looks like magnesium and sodium are losing electrons to be like neon, and oxygen and fluorine are picking up electrons to be like neon. So they all have 10 electrons. We could be asked this question: what is the size of these guys in order of from smallest to largest? Well, in order to answer that, it might not be, I'll tell you right off the bat, you're like, well, magnesium should be biggest, okay, because it's got 12 protons. But I'm going to show you why it's not. So how many, even though magnesium has lost, the Mg plus 2 cation has lost 2 electrons, what does its nucleus look like with regard to protons? How many are there? Magnesium plus 2 cation, how many protons in its nucleus? It's not trick question. 12. Thank you. Yep. Oops. Let's start the other way. So oxygen, it picks up 2 electrons, so now it has 10 electrons, but how many protons in its nucleus? 8. Yep. How about fluorine? How many protons in its nucleus? 9. Very good. And then let's go on to, I think, sodium. How many protons in its nucleus? 11. And then now magnesium. It's got 12 protons. So now we have a situation. I'm going to change this from beryllium. Okay, and I'm just going to go ahead and put plus here, positively charged. And we're going to say it's all isoelectronic. We have an assortment of positiveness here. We have 8 protons for oxygen all the way to 12 protons for magnesium. Okay, so now they all have 10 electrons that are being pulled in to create a size. I already told you a minute ago that actually the magnesium plus 2 cation, not the magnesium atom, but the plus 2 cation is actually smaller than the oxygen anion. The way it works, and it has to do with the attractive forces kicking in, is if you were to rank oxygen and then fluorine and then sodium and magnesium, this has the most attractive forces. Most attractive. And this has the least attractive. And we said a minute ago, if your attractive forces decrease, then your size increases. So honestly, I know it feels kind of weird, but your isoelectronic oxide ion is going to be larger than your magnesium cation. All right, and here's how they go in picometers. I just like the word picometers. That's funny. Okay, so ionization energy, ion. You see the word ion in ionization energy. So what we're talking about here basically is stripping an electron off. That's ionization energy. Specifically, the energy you need to zap something with in order for an electron to be kicked off. That's ionization energy. And so the zapping energy is in kilojoules per mole of electrons that you kick off. So if you're zapping something with energy and kicking off an electron, when we look at the metals versus the non-metals, we said the metals are all kind of cool with that, kicking off an electron or 2 or 3. Metals do it great. So in general, we're going to see that metals generally have low ionization energies. That means you don't have to zap them with much energy in order for them to kick off an electron. Relatively speaking, metals have low ionization energies. Notice the slide doesn't just say metals have low ionization energy. It says metals have low first ionization energies. So in here in a minute, I'm going to try to kind of talk you through. It's possible to take something that's already a +1 charge, zap it again, you kick off another electron, and now it's a +2 charge. That energy to kick off the second electron actually is called second ionization energy. So in this part of material, we're a lot about taking the periodic table again and showing trends. The trend we looked at was, we said, and I'm going to talk about something called electron affinity here in a minute. We talked about something called chi, electronegativity. We said electronegativity for the group A elements, and that's what this is. Just take the S block and the P block, squish them together, take out your D's and your F's. You have electronegativity increases this way, and electronegativity increases this way. Well, ionization energy has the same trend, which is kind of fun. Makes your life easy, I think. So ionization energy increases the farther you get from the metals, because we have metals over here, non-metals over here. Okay? And then ionization energy increases again, like electronegativity, as you go up. There's those two. Notice that there are some exceptions in the 3A, which would be with the like aluminum, and the 6A, which would be like sulfur and oxygen. So can you kind of see that in this graph? You kind of see the bumps. What do the bumps all have in common? What do neon, helium, argon, krypton, xenon, and radon all have in common? They're noble gases. They're rare gases. Yep. So you can kind of see down here, like this is your group 1A element for that period, rare gas. Group 1A element for that period, rare gas. 1A for that period, rare gas. Okay, so that's kind of how it goes. Ionization energy increases across the period and as you go up. Here's some more look at ionization energies. Now these again would be kilojoules of energy per mole of electrons that are kicked off. Again, looking at just the group A elements. So 1A, 2A, this is your S block, and here's your P block. You kind of see it stepping up. And this, hopefully you recognize, this is the box arrow notation of the elements in the second period. This is, I think, just kind of showing us where the metals, which would stop. So for lithium and beryllium, it's easier to kick off the 1 and 2 electrons than it is, for instance, for oxygen, it's easier to bring into electrons. Okay. I never get that slide. All right, so I mentioned there's first ionization energy, second ionization energy, third ionization energy for the same species. And in each case, what you're doing is kicking off one more electron from that used to be a neutral atom. So the first ionization energy is energy needed to take off the first electron. Second ionization energy is the energy beyond, or the new energy required to kick off an electron from that +1 cation, basically. We have a third ionization energy, fourth ionization energy, etc. But for the same species, and this probably makes sense, for the same species, once you have an electron gone and you have a cation, it's harder to go after that next electron. So what this says is that the first ionization energy is the least, and it gets steadily harder to kick off an electron from that cation. So I have a couple of videos to kind of show you. We're going to pick on magnesium, who hopefully know a little bit about chemistry. Why is there such a jump between the second and the third ionization energy? Yeah, you're dipping into what's already stable, the next energy level. It already had a rare gas configuration. Yep, exactly. So along those lines, we have this table, which I don't think is in your, it's not figure, that's not from your OpenStax. But we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So these are all in period number 3. So you guys would tell me a +1 cation, a +2 cation, a +3 cation. And then over here, chlorine is a -1, -2, -3. Silicon somewhere between. It kind of goes back. It could potentially go either way. So with magnesium, what we saw, or wait a minute, starting with sodium, you see where that big jump, it's almost tenfold. After you have a sodium +1 cation, the second ionization energy is crazy big. Magnesium, we already kind of looked at that. Our jump was between the second and the third ionization energy. And so not so surprising for aluminum, the big jump is between the third and the fourth ionization energy. Silicon, between the fourth and the fifth ionization energy. Now we're talking some big energies expended. Notice to kick off the phosphorus, the first electron, it takes 1012
kilojoules per mole of electrons kicked up. Okay. Sulfur, chlorine, and then argon. Oh my goodness. It can be done though. I look at data like this and sometimes I'm like, who does that? Who goes to a lab and strips off electrons and measures the energy? Okay. So that was ionization energy. Ionization energy. And that was kicking off an electron. Kind of the opposite of ionization energy is electron affinity. So this is where at my desk, when I get ready for this part, I smile because I'm like, if somebody says they have an affinity for chocolate, it means they love chocolate. So with this electron affinity, that is basically a measure of energy required to give somebody chocolate. No. It's the amount of energy that's associated with adding electrons onto something that may or may not want electrons. Okay. Now, the thing about electron affinity, adding electrons to a neutral atom or to something that's already an anion, electron affinity can sometimes be endothermic, requires energy, and sometimes electron affinity can be exothermic, where energy is released. I'm telling you, if I get chocolate, energy is released. Okay? So actually, unlike ionization energy, which is always endothermic, this one can go endo or exothermic. Speaking of, when we talked about your heats of reactions, if something was, if your delta H was negative, was that endo or exo? Delta H was negative. It was exo. So if your delta H is negative, it's exothermic, it's giving off energy. And so here in a minute, we're going to talk about enthalpies of electron affinities. Okay? So if they are negative, then that means that it's exothermic. That would be like me and chocolate. Okay? So that means energy is released. Now, exothermic energy released, what this says is it forms a stable ion. In other words, it wants to do that. It's favored. Okay. And then if your change in enthalpy is associated with electron affinity, adding electrons onto something, if that's positive, then that would be endothermic, and energy is required. And this actually then forms something that is not favored, forms something that is unstable. So when you look at these electron affinities, you're going to see positive ones and negative ones. The more negative it is, the more favorable it is. So instead of kind of giving you the negative and positiveness of it, you figure electron affinities. This is now not the numeric value, but just the term affinity. Like I have an affinity for it. So if we look at the nonmetals over here, these guys are more into getting more electrons. So when electron affinity increases like this, then electron affinity actually increases up the group. So now we have 3 trends, right, that have the same, for group A elements, increase across, increase up. So electron affinity. Like I said, or like, well, what it says in italics here, think of that as, if possible, it's more exothermic, energy is released. It's a happier, more stable sort of situation. But it's funny because value will be more negative. Cool. So electron affinity can be thought of as an atom or an ion, if it's already got extra electrons, want to get more electrons. Okay. Relatively speaking, who wants to get more electrons? It's the nonmetals. So they're more negative, but they're higher. The nonmetals will have a higher affinity, more negative. I think we already kind of said this. So this is kind of, there's your enthalpy associated with adding electrons. Okay. Electron affinity, delta H electron affinity. If it's negative, then that's forming a stable species. If it's positive, that's exothermic. If it's positive, it's endothermic. And once you've done that, added those electrons, it's not happy. I can't imagine anybody not liking chocolate. Okay. So you can kind of see, these get a little confusing for me, but in general, the trend is there. I don't think they're not as clean by any means as like atomic size that we're going to talk about Monday. Electron affinity, the S block, P block, minus the halogens. We don't want anything. So this is a little bit out of order, so I apologize. Now I'm just going to leave this one for, this was really out of order. So I'll pull this one in on Monday, talking about atomic size. And then that leaves us to, dun, 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 part 5. So this gives me a little extra time to go do some more problems. And any questions about what's due and all that. And when did I made, if you want to do extra credit by cutting out those flashcards, 10 points. And then also doing that worksheet. And I made them do the Monday after Thanksgiving. All right. Have a good weekend.